Okay, so these are some scenes from last chapter. I hope you still don't forget what we were studying. And this is one way to implement the LL analyzer. So please remember that this was necessary because at some points we had ambiguity. We didn't know which one of the rules or the arcs to follow. And this led us to the need of having to analyze every way, every arc. And of course, this can grow exponentially. You know that when complexity grows exponentially, a simple or relatively simple problem can take ages, and literally ages. I mean, by million years, if it gets too complicated, of course. So we want to avoid that. One strategy or one way to avoid this is just to have some look ahead, like in this table. And remember that by using this look ahead, by seeing which one of the symbols we have ahead, at least one, then we are able to select or to choose a rule, one of these arcs, making the problem much simpler. However, we had the inconvenience that for some grammars like this one, an LL1, a look ahead of one symbol was not enough. So we needed more than that. In this case, we have an LL2, which needs at least two characters ahead, two symbols ahead to be able to take a decision. Then we saw a problem. We saw that for this language, which is the union, I need to select. Oh no, this is, my pencil is dead. Okay, I will select with my hand. So in this case, we have, we need to see two characters ahead. Okay, now this, we have a language which doesn't matter how many characters we look ahead, because this is infinite. We should need, we need to see an infinite number of characters ahead, because this n can get very, very large, infinitely large. So an LLK for this language is not feasible, so that we need a different strategy. And this strategy is called LR parser. An LR parser is based on this different way of analyzing the language, which is very similar as before. However, we need to insert first the hash into the stack, and then we start operating by inserting each one of the symbols until up to a certain point, and then we start reducing them. So this kind of operation is called push, when we insert each symbol and then reduce. This push is also called shift. Shift because we are shifting the input. When we read this symbol, then we shift the input to the next one. So we have two operations, shift and reduce. And that's it. So here we had to finish our last class. So we will start building from here. So today I will show you how to build an LR parser, which is a little bit complicated, but not that much. I think it's kind of fun to do it. And all this information comes from the Appendix A of the Brookshire book. So in case you want to review it later, you can just refer to Appendix A. So actually, Brookshire says that this is a way of building an LR1 parser. However, other authors refer to this as an LR0, because of course it's trying to look ahead, but it's not consuming this number. So if you want to see the same way of construction, you need to refer to it as LR0 with other authors. So remember, we have other reference books, which are the Sipser or the Ullman, Aho, Seti, Ullman, all these nice people. then you refer to this as the LR0. Brookshire is the only one that refers to this as the LR1. However, don't worry, we won't see too much complications here. We will just see the method which corresponds to the one that Brookshire is explaining to us. Okay, so here we go. Oh my God, no, we cannot go. I still have discharged my pencil. So yes, that's too bad, but it charges very, very quickly. Okay, so on the meantime, I will, instead of drawing, I will copy paste our grammar of always. So you know which one is a grammar of always, right? The famous Zaza. I can see in your faces that you already know it. So here it is. This is our friend Zaza. And the beginning of this consists on adding a new rewriting rule. This rewriting rule will be called S prime and consists on adding this rule. So our marker will go something like this. When we are at the beginning of the table, of the rule, sorry, we will have something like this. If we move this cursor ahead, like reading the Z, then we will have something like this, M and Z. And if we gradually move this, showing that we are analyzing the rule, is like if it is walking through the rule. And we will have the initial position of the rule. This is called the initial form of the rule. And you can guess how the last one is called, the final form of the rule. Of course, for shorter rules like this one, we will have the initial form of the rule as this and the final form of the rule as this. And you can guess how the other rules will behave with this cursor. So you can see here, I'm drawing it like a small caret. You know, the caret is like the circumflex accent in some languages. It's like a small triangle. And other authors, again, if you go to study this in Zipser and other authors, you will find that they represent this with a dot, like something like this. So it's exactly the same. It's just like a cursor. It's showing in which part of the rule you are now, and it will be useful in order to build this analyzer. So we will begin by adding a state. Let me change my screen because we will need a lot of space. So we will start by forming a DFA. So we will use the DFA in order to build an LR parser. And remember that an LR parser is parsing a context-free language. So perhaps you will see a bit of confusion here because a DFA is used to analyze a regular language. So because we will be building a DFA, you can say, how come are you using a DFA to parse a context-free language? Wait, no, because you can say this is a regular language and this is a context-free language, which of course is more powerful, right? So by the way, I said, wait, no, I didn't say wait, because it sounds the same, right? But well, okay, bad joke. So wait, no. So in order to avoid this confusion, you have a DFA that of course works for regular languages, but in this case, we will use it only as an auxiliary to build an LR parser. The DFA that we are building will not be used to parse the whole language. Only we are building a table that will be our auxiliary table in order to parse a context-free language. You will see this. So we will start by building a DFA. So this is just for you not to get confused with this construction. We start by adding a rule, which is the new rule we created, which is S prime produces S. However, please note that we are adding this rule in its initial form. The cursor is standing just in front of this S. Now, for each rule that has a cursor standing in front of a non-terminal symbol, like in this one, so the cursor is just before a capital letter, we have to expand this capital letter, these non-terminal symbols, into all of its rules, beginning as a, starting as a initial form. What do I mean? Then I mean that we need to add S and the form of this rule, the initial form of this rule, and that's it. Please note that if here we had a capital letter, if here we have a non-terminal symbol, we need to expand it as well. Because this is a terminal symbol, we do not need to expand it. So we have finished the creation of our first state. We will be repeating this several times, so don't worry if at this point you are not completely getting the idea. You will get it, I'm sure, because this is a bit repetitive process. So let's continue working on this. Now that we have this cursor, this will allow us to walk it or to move it in each of the rules. So there are several ways to walk. One is walking this to here, to this position. Another one is walking this, just advancing one symbol. This means that this DFA will have two outputs. One, when we walk over S, and this will lead us, the cursor moving from here to here. So we will have the first rule expressed as S and in final form. Also, please note that whenever we reach a rule in a final form, we will have an accept state. So this will be an accept state. Another way of walking, we cannot walk further this one, and we can walk only one symbol at a time. So if we walk this one, we ignore this rule, is this way. If we walk this one, then we ignore this rule. So if we walk by using Z, then we will have the second rule with the cursor moved just one symbol. So you see, we moved this one from here to here because we had a Z as an input. And then please note that we are standing just in front of a non-terminal symbol. And we said before that whenever we are standing in front of a non-terminal symbol, we must expand all the rules corresponding to this terminal symbol. We will add all the rules corresponding to M in its initial form. That is, M is AMA and M is also Z. So we added these two rules that are highlighted in green just because we are standing in front of a non-terminal symbol. That's why we needed to add these two rules. And that's it. We have finished expanding all possible rules here. So we have finished drawing this symbol. And now we need to see which are the symbols we need to walk by. We can walk by M or walk through M. We can walk through A or we can walk through Z. All these then will represent the possibilities of advancing our cursor. So we have a movement in M. That's it if we move this one. And also we can move by A, and we can also move by Z. So again, where did I got this M, A, and Z from? I took it from M, from A, and Z. So it's easy. You just need to see which are the symbols that are just before, that are just after our cursor. All possibilities are need to be added here, M, A, or Z. No other possibilities. Okay, so in case of M, what will happen if we move M? Well, we will have this rule advanced here. So we will write S, Z, M, the cursor moved here, and Z, and that's it. And now you know it, because we are standing just in front of a non-terminal symbol. We need to expand it, right? So we will expand the N. N is expanded in its initial form as BNB. And of course, it can be Z, because we have 2 rules for N. If we have 10 rules for N, then we need to add all 10 rules for N here. Okay, and we have finished expanding this node as well. So before we focus on this one, I will move to this one, to this A, and see what happens if we move A. If we move A, then this M will turn into A cursor MA. That's it, M, A, cursor M, A. That's it. And again, I need to expand it because I'm standing just before a non-terminal. In order to expand it, then I need to add the same rule, but in initial form. So you see that two rules can be together, but they are in different positions. This is in not in initial form, and this is in initial form. So why this happened? Because here I'm standing just before an M. So we have these 2 additions here, the AMA and Z, right? Okay, let's pause for a couple of seconds for you to synchronize. Okay, and now let's see what happens if we move through Z. Moving through Z will happen only in this rule. So when we move through Z, we will have M, Z, final form. M, Z, final form. So given this, we do not need to expand this state further, and we have finished. That's it. And remember, we said that whenever we reach a rule that is in a final form, then we need to make this an accept state. So this is an accept state as well. That's it. We have finished then creating all the possible outputs for this state, M, A, Z. Remember that they come from M, A, and Z, and there are no more possible outputs. Okay, let me erase this part so that we have more space. That's it. And now we need to examine each one of these, both M and both A. I'll begin by analyzing this one. And just to make it clearer, we are adding these rules just because we were standing in front of M. So we need to add the corresponding rules for M. Okay, so what are the possibilities of moving out from this state? We can move if we have an M or an A or a Z. If we move through an M, then we will have this. We will have M, A, M, A. That's it. And there are no more rules to expand, so we can close this state. This is not a final form of the rule, so this not need to be an accept state. Okay, so this was for M. What happens with an A? Oh, what's that sound? Oh, very strange. I don't know. If someone wants to say something or ask something, please open your mic. I cannot identify what happened. No idea. Okay. Okay, so we were here, we expanded M. Now we need to expand A. And now pay attention. What will happen if we expand A? If we expand A, remember that we are expanding this second rule here. So we will have this rule in form A cursor MA. which is in this way, M, A, cursor, M, A. And then, as before, we need to expand this M. In order to expand this M, then we add this M in its initial rules. So we can write Z like this. And now you can see that these three rules are exactly the same ones as these ones. So this state is exactly the same as this one. So maybe we can just circle it. So if you see these two states, they are exactly the same. Then it means this A goes back to itself. We don't need to add another state because this is the same as this one. So whenever you find this, that you have exactly the same rules in one state, it means it's the same. So we will just loop back this A. And that's it. And we erase this one, right? Okay, so just one final movement here. We have a Z. If we move this Z, then we will have M, Z final. And this is an accept state. But again, if you see this state we have here and this state there, they are the same. So again, we won't create a new state. I will just connect this Z with this one, and then we can just erase this state. Okay, so far, are you okay? Are you following me? Okay. Let me see. There are no. Let me close. Ah, I know what was the sound. It's my email. Sorry for that. Okay, so let's continue. We have so far worked on this, and this state, and let's follow this state because it's relatively simple. We just need to advance or to move this final cursor. So this will become M, A, M, A in a final form. So this will be an accept state. This is not used before, so we can create it, and this will be a new state. And that's it. We have finished with this line. So now we need to finish with this part. And again, we can advance on N, B, or Z. Let's do that. So if let me make this a little bit smaller so that we have room for all the things that we need to draw. Still we need to draw. That's it. Okay, so we will move with N. If we move with N, then we need to add ZMN because we have just passed through M. We are moving this cursor from here to here. So now we are ZMN Z, and then N goes the same. No, sorry. We don't need to add this one because we are just moving with N. So that's it. We move with N, and that's it. We don't need to add any more because we don't have anything to expand here. So that's it. We are done with this one. And sorry, that's horrible. Okay, that's not so horrible. Okay, so we can also move with B. So I will put this here with B. And if we move with B, we will have N, B, and B. So you can see that we moved this cursor from here to here. That's here, okay? So we need to expand this one because this is just before a non-terminal symbol. We need to add all the rules for N in initial form. So B and B, and finally Z in initial form. And that's it. We have finished creating this state. And finally, we can move with Z. Let's move this here, Z. And with Z, we have this in final form. And also, you know what happens when we have this in final form. This will be an accept state. That's it. Very good. So now let's finish this one because it's very easy. We just need to move the cursor to the last position by moving through Z, and we will have Z, M, N, Z cursor. And again, this is a final form, and thus is an accept state. Okay, now we have only this state, and we can see we can move again through N, through B, and Z. Why? Because we can move through N, B, and Z. What happens if we move through B? We just advanced it and we have something like this. No need for more expansion. If we move through B, which will be this one, we will have the second rule rewritten as N, B, N, B. And of course, we need to expand again these rules because we are in front of a non-terminal symbol. So we will add N, B, N, B, and also N, Z. And that's it. And again, you can see this is exactly the same as before. So we will add a loop, or we will change this for a loop. So this will be B. That's it. And finally, for C, we have the last rule, which is N, Z. It's a final form, so we have an accept state. And I think we have finished. That's it. So that's not so complicated, right? Okay, now let's convert this into a table.
Teacher, there is one left.
Yes, there's one left. Which one? Oh, yes, thank you. This one, right? Thank you. So we will finish by adding a B, and B final form. Okay. Now we are done, right?
Also, the state n goes to C final form is repeated.
Okay, very good observation. I even could say I did this on purpose in order to see if you were paying attention. And maybe you would believe me, but I think no. Okay, that's it. Thank you very much. The state is repeated, then we do not need to add it again. Thank you for paying attention. Okay, so now I will make this again smaller again, because now I want to create a table from this. So exercise 1.
Yes.
We write a program using a repeat until.
No, the one that says with the alternative process. No, it's page 130.
Okay. Using the alternative process for constructing a pushdown automaton from a context-free grammar, construct a transition diagram for a pushdown automaton from the grammar below. Yes, yeah. And the alternative process is the second one that we did. I don't know if you want to present your homework and we can check it.
Okay, let me just search it. Yeah, it says that I can't share my screen because someone else is. Yeah.
Okay, I have stopped sharing.
this one.
Okay, well, the grammar is x as z or z or y as z. And why did you add uh, these lambdas and the first one, which is lambda y z?
Um, because yeah, because if there's the short string just like YC and XC, that's my doubt.
Yeah, oh, I see, because of the s goes to lambda, right?
Right.
Well, however, remember that lambda does not need to be added here as a by itself. But it's a very good question. What happens if we have a lambda rule here? Well, first of all, we need to allow just adding, it means it will accept the empty string. So we need, according to the previous diagram, let me go back. Remember that the first transition is to add an S, which is not correctly drawn in the diagram, but in yours is okay. So you are adding, first of all, you are adding
Yes.
a hash. Mhm.
Yes.
Then you need to be able to add an S as in your in that arc that you are showing, and then you will just remove the S and finally remove the hash. That's correct. And then what happens if you have only the S? Then you don't need to add the first arc because you already have the final one, which means that in every moment you can just add an S, so that
Okay.
it means that if you need to consume, let's say, for example, X or Y as the, I need to point, let me see if I can point using your screen. I think I cannot annotate. Okay, can you see my annotations?
Yeah.
Okay, so, oh, sorry. Okay, so what I'm saying is that once you have this rule, which is okay, because it means that you can just process the input by first adding this hash. Then you add the S, then you remove the S and remove the hash. And effectively, you will have, uh, you will be able to accept the empty string. Then what happens if you have something like YZ? Then you will be trying to uh, read a string starting by YSZ. And at any point, you can just insert this S here so that you will be able to change this YSZ into S, right? Then you don't need to add this rule because you have already added this one. So this is okay, and you don't need this one. Oh, you don't need to add this one. This is okay, and with that is working properly. And also you don't need, I think this is on the same fashion, because you are trying to parse what happens if you find only an xz. So you don't need also this one because you have the function by this one, okay, by the one which is circled. So this is okay. The other ones you don't need to add them. And finally, you're adding x, you're adding y, and you're adding z. So the final solution will be without these ones. Yes?
Okay, so we don't need like loop to exchange like a pair of characters from the stack.
In this case, you can start, for example, adding x, and then you will generate an s out of from nothing, and then you will add
Okay.
a y. So once I recover my screen. Maybe I can, or maybe I can
Yeah.
try to do it here. Suppose you want to, can you share again, please,
Ah,
in order to illustrate this last thing? Thank you. Yeah. Okay. So let me annotate. Okay. So suppose we have this x, y. No, it's not x, y. X, z. X, z string. And suppose we have our stack here. So the first thing we will do is to add a hash into the stack. And then we will need to process x and z. First, by using this rule, we can just consume an x from the input and add it to the stack like this, right? And then, because we have this rule that allows us to add an s into the stack whenever we want, then we will add this s here. And we have not processed yet this z. And then we will process this z, moving our head to the final position and adding it to the stack. And we are adding it to the stack by using this rule. We consume this z from the input string and push it into the stack. And now we have xsz, and we can convert this into s. So our stack will change into s. And now we are able to follow this arc here, just taking out the s from the stack, and finally take out the hash from the stack and leading us to an accept state, right?
okay, right.
So I think this way it's a bit clearer.
Yes.
Okay, so now you can stop sharing. Thank you.
Yeah, thank you.
Okay, let's see if I can share again my screen. And this is it. So now I will try to make this smaller. And we will use this as a reference. Okay, so now I'll try to draw a table. And for drawing this table, we need to consider the state as a vertical. I cannot draw with my hand. How come? Let me see. So I cannot draw with my finger. So bad. Let me think, what can I do? Okay, so I know. So please, if anyone has another question, please help me while I'm trying to recharge my pencil. So this is so bad, like everything is rechargeable. So That's when, just imagine we are in the middle of the class and my the marker is empty, it's dry, and I need to go to DTE to ask for a new marker in order we can continue to the class. So this is the equivalent.
Yes, we have a question though.
Yes, please.
In equaling the homework in the problem number 4, I don't remember the page. Let me check.
Mhm.
Okay, it's the page 118.
Yes.
I don't know how do this the analyze symbols.
Ah, this LL1, right?
No, the problem number 4, page 118. Yes.
Okay, then it's 19. Okay, yes. So so it asks how many symbols, and we already know that. Let me annotate here. And now I don't know how to annotate here. Okay, here it is. So you can see here, at least you cannot use an LL1, because if you do that, you still have ambiguity. And also, you can see that, oh, that mode, right? Okay, let me stop annotating. Okay, so we have this. So you cannot use an LL1 because it will be the same ambiguity. So you need something like, you need to expand the rules. So if you expand the first one, which says X as Y, you will have two different rules. You will have both. You need to insert the rule itself as X, X as Y, Y, because you are inserting the rule in itself, and you need to insert the second one, which would be X, X, Y, Y, right? So out from this one, you are obtaining two different rules. This is one, and this is the second one. So far, if you do this, again, you will have here that you cannot use, at least for this part, an NL2. Let's see what happens if you do a further expansion. Then you will need to expand this first rule again into two different ones. Why two? Because you have exactly two rules for S. So if you expand the first one, you will have X, 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 S, Y, Y, Y. Oh my. I cannot move them. Okay, let's do that. Okay, and for the second one, you will have this. S, X, 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 Y, Y, Y. And again, if we examine the first three symbols, we will see that it's not possible to apply an LL3. So we cannot do that for an LL1. We cannot do that for an LL2. And we cannot do this for an LL3 either. And also we can see that if we keep expanding this one, we won't be able to do this for an LL4, an LL5, etc. So precisely this is one of the examples that we saw last time, that we are not able to build an LLK parser. So the answer here is we cannot build an LLK parser. And then we saw that there was an answer. The answer was to build an LRK parser. So that's what we are seeing today. Actually, your task will be, your homework will be to build an LR parser with the elements we are studying today. Okay?
Okay. So thanks.
Welcome. Thank you for asking. So let's see if we can use our pencil just as before, our marker. I hope it will work. Yeah, good. So let me share. So we will build a table. What does this table has? Well, we need to number all states. I will change color and number all states. They can be numbered in just any way you want. However, I will try to number them in the same way as Brookshire did, just in order for you to review easily if you check the Brookshire. So this will be state number 1. This will be 14th. This will be number 2. This will number 7. This will be number 3. Number 8. Number 12. Number 4. Number with N goes to 6, and this is 11. This is with B. 4 and B goes to 5. 5 and Z goes to 9. 5 and N goes to 10, and 10 and B goes to 13. That's it. So don't worry if you wonder where the hell did the teacher took these numbers from. Well, it's actually from figure 2.37 at page 127, just if you want. Okay, now we will convert this into a table. First, on the left part, we will use all these numbers, not so thick. So let's put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Why 14? Because we have 14 states. And on the top of each of this table, we will have the numbers, the symbols corresponding to it. So we will have here what happens for symbol A, for symbol B, Z, end of string. And also we need to put here what happens with the non-terminal symbols, S, M, and N. So given this, we can draw our table. I will just draw the horizontal lines and vertical lines. So yes, I'm cheating because I am using something that straightens up my lines, but this is very convenient. And also I will use it for this one. That's it. What a nice table. Okay, so what I'm going to represent here is something like the transition table, where we have for each one of the symbols here what happens. So if we are on state 1, if we have a Z, we have a displacement to the state number 2. So with Z, I will annotate shift, and go to number 2. The S will mean shift. And shift means read a letter from the input string. So shift number 2. Then if we have also an S, we will go to state 14. And here we won't do a shift. We don't read the input string. In state number 2, we have with a Z, we have a shift and go to number 7. So 2 and Z, we shift to number 7. And also we have with an M, we have to move to state number 4. So 2 and M go to 4. And 2 and A, shift and go to number 3. Shift and go to number 3. And that's it. There are no more changes. For state number 3, this one, if we have an A, we will shift and stay at number 3. If we have a Z, we shift and go to number 7 as well. And if we have an M, we move to number 8. In state number 4, if we have an N, we will move to state 6 with an N. Move to state 6. From 4, if we have a B, then we shift and go to number 5. Then 4 and A and B, sorry, shift and go to number 5. And if we have a Z in 4, we will shift and go to number 9. Shift and go to number 9. And that's it. In state number 5, here, which in order to fill this one, if we have an N, we move to number 10. If we have a B, we shift and stay at 5. And finally, with a Z, we shift and move to number 9. Shift and move to number 9. And finally, finally for this set, if we are on state 6, if we have a Z, then we shift and move to number 11. And that's it. There are no more outputs. Then we will change things a little bit here, because if we are on state number 7 here, then we have a final rule. Whenever we have a rule in its final form, then we won't do a shift. So that's why I say there is a change of a bit of change of game here, because we won't have shifts. Well, we will start mixing shifts. But for state number 7, because it's an accept state, then what we will do is add for, oh my God, let me make smaller. For all A, B, or C, for anything coming, we will just do M. We will do a replacement of M goes to Z. That's why some other authors call it an LR0, because we are not doing different actions regarding each one of these. However, we are using the construction system in order to know if we have to shift or reduce. Brookshire called this LR1, I insist. However, we will see only this method, the LR0, which has exactly the same rule regardless of A, B, or Z. Again, go back to number 8. In number 8, this is not a final form yet, so we still need to see what happens with A. 8 with A goes to 12, so there's still a shift. 8 with A shifts to number 12. For number 9, here we see it's a final form, so we will do the same for the A, B, or Z. N goes to Z. For state number 10, not yet a final form, so we need to see what happens with B. It will be a shift to number 13 with B. Shift to number 13 with B. State 11. State 11 is also a final form. However, we have an exception here because we are using the S. So whenever the S rule comes to a final state, then we won't write this here, but here. So the only times we will use end of string will be whenever we have the final form of the S original string, or whenever we have the final form of the S prime rule. So in this case, we have the S, and we will write here in state 11, when we reach this one, we will substitute S for Z, M, and Z. Sorry, I invaded a bit the other column. In the state number 12, it's a normal final form, so we will just proceed as before. We will change M for A, M, A, and that's it. For state number 13, it's a final form as well, so we will proceed as before. We will add N, B, and B. And finally, state 14 is also of exception, as we saw here, because whenever we reach the final form of the S prime rule, then we will have to write accept here on the F of end of string. And that's it. We have built our wonderful table that will allow us to parse this our grammar friend. So let's see how it is working. Suppose we have a string. We will have Zaza. Yeah, how original, right? So let's have our stack here. Our stack is well below because we will put a lot of things on top of it. So let's begin by adding. In this case, we won't add a hash, but we will add a number 1. What this means, because we will use this 1 corresponds to this row. We can forget about this, but I won't erase it because we have still some room on this whiteboard. However, we have this 1, and also we are watching the current symbol. We are watching that we have a 1 and a Z. So it says, if you have a 1 and a Z, then shift it and move to state number 2. By shifting, we mean consume it, move to the second symbol, and move to state number 2. So in a funny way, we have here the states represented by numbers. So we insert the number 2 into the stack. Yes. So now we are here, number 2. So if we have we are number 2 and we see an A, we see 2 and A, it says shift it and move to number 3. And by shifting it, it means consume it, move the head, add it here, and move to number 3. Nicely, we have something that allows us to remember which is the state we are in by adding it to the stack. So now we have 3 and Z. Let's see what our table says. 3 and Z says shift it and move to number 7. So we will shift the Z and move to number 7. And now we have a 7 and an A. 7, and regardless of what is here, it says, okay, now you can change the Z into an M. See that we are using the rule backwards. It says, if you have a Z, you can convert it to an M. So yes, we have a Z here. It doesn't matter we have this symbol here, it's just a marker. So what we will do is consume this Z and change it for an M. Why? Because it says Z, you can change it for an M. All rules here will be used in the reverse way. So this Z we had here will be changed for an M. Now, if I erase these ones, our stack will be like this. Okay, now please consider the last 2 ones. We have a 3 and an M. And if we check into the table, when we have a 3 and an M, it says change it for an 8. So now I will take this out and change them for an 8. Sorry. And then add an 8. Like this, on top of that. So now we have still the same case. We have 8 and an A, 8 and A. So 8 and A says 8 and A, shift it and move it and move to 12. We shift this A and then move to state number 12, like this. And now we have 12 and B, 12 and B. So if we go to 12 and B, we see a replacement again. And please remember that we will have replacement just backwards. AMA goes to M. If we watch carefully our stack, we do have AMA here. So we will change all that for M. So I won't erase now so that you can remember what was happening. So I will just replace this. Sorry. So I replace this AMA will be replaced with M according to the rule that is in yellow. Now, remember that when we have a non-terminal symbol on the top of the stack, we need to combine it. So 2 with M says add 4. Okay, so we add 4 here. And now we are able to compare 4 and B. We have not consumed B, so we can compare 4 and B. And the rule says 4 and B, it says shift it and move to 5. We shift it and move to 5. And now 5 looks 5 and Z, 5 and C, shift it and move to 9. So we shift it and move to 9. We need to compare 9 and B. And 9 and B says, please change the rule again. So let me mark this with a different color. We are comparing 9 and B, and 9 and B says apply the rule that says N converted, Z converted to N, meaning that this Z will be converted to N. And now we have 5 and N, 5 and N go to 10. Go to 10. And again, we compare 10 and B, 10 and B, shift it and move to 13. Shift it, B, and move to 13. And now we don't have too much space here. So let's erase this part. Shift it and move to 13. And 13 and Z says 13 and Z. Again, let me highlight this. It says 13 and Z is 13 and Z. Change B and B to N. So we have B and B, all these will be changed to N at this point. So let me rewrite everything so that it gets a little bit less cluttered. I hope you are getting it. And let's move it a little bit to the left. So now our stack is 1Z, 2M, 4N, and we have 4 and N, 4 and N goes to 6. We add a 6 here. 6 and Z, it says shift it and move to 11. So we will shift this Z and move to 11. Yes, let me move this a little bit to the left so it doesn't confuse you. Okay. So now we have Z, 6 and Z, move to 11, shift it and move to 11. Now our head is end of string, and 11 and end of string, then it says change Z, M, N, Z, Z, M, N, Z, change it for S. So we will change all this just for S. So we have 1 and S. because we consume ZNMZ, this. So now we have 1 and S. 1 and S says move to 14. And finally, 14 and end of string, accept. And this is it. So nice. So it's complicated, but please note that we didn't have in any moment, we didn't have to think of the ambiguity of this grammar. Yes? So this is the important part of this, that by constructing these kind of tables, you won't need the use of ambiguity. This works very well with an as an LR parser. Brookshire, I insist, Brookshire says it's an LR1. Other authors call it LR0 because of this part. Because of this and this, because we are not differentiating what happens by using each symbol. That's why it's called an LR0. Okay, now that you know how to build this, you will do your own. So the homework will be to build an LR parser for the language LXN union XNYN. And in this case, do not consider the empty string because it's easier. Otherwise, you will be struggling with the empty string as in the homework, as the question of today. So let's avoid that. So remember that we saw, no, that's very bad. Precisely, this one cannot be built with any LR. So I am asking you an impossible. So again, no way. That. Okay, sorry. So let's build it for X and Y n, and n belongs to the positive integer numbers. Okay, so sorry for that. I just forgot that you cannot build. It is not possible to build an LRK parser for this language. Actually, this is the canonical example. You can for this language. Okay, so the question of today precisely was about trying to build an LL parser for this. An LLK parser cannot be built for this language. But you can build an LR parser. So your homework will be to build an LR parser for this language. That's it. So it's clear, the homework is clear, and how to do it, how to solve it. You need to build a table as we did today. And in order to work for this language, you need to find the grammar for it, which is not so difficult. Then you start building all the possibilities for the grammar, and it will be much smaller. The table will be much smaller than the one we saw today. So I hope it will be relatively easy. And well, that's it.
I have a question about if you are going to upload this class to the model, if possible.
Yes, of course, with pleasure. it had a lot of failures. I'm sorry, because I ran out of battery, but yes, I will upload it if it works for you.
Okay.
So yes.
Thank you very much.
No, you are welcome. And well, I need to leave now because we have a meeting, colegio, a council meeting at 1 p.m. So, well, I'm so sorry. As always, I prefer to be with you, but also I need to go to other teachers' chores. So, well, thank you very much for your understanding. See you next Thursday. And please work on this now that you have it fresh. And I will try to upload this as soon as possible, to upload this explanation.
Thank you, Doctor.
Thank you.
See you.
Thank you. Bye.
You're welcome.
Thank you. Bye-bye.
Thank you, Professor.
Bye
See
bye.
you. Have